this is falling. Okay. Yeah, that's the time. Okay. Yeah, we can start if we're not expecting anyone, we can start. Sure. Okay. Yeah. So, okay, sure.
Good evening, everyone. Welcome to the another session of the Network Seminar Series hosted by the Center for Networked Intelligence at the ECE and RBCCPS IASC. It's my pleasure to introduce today's speaker, Professor Ganesh Ghalme, and he will be speaking on learning in the presence of strategy. Dr. Ganesh Ghalme is an assistant professor at the Department of AI, IIT Hyderabad. He was a postdoctoral fellow at the Game Theory Group, Technion Israel Institute of Technology, Israel from July 2020 to March 2022. Prior to that, he completed his PhD from IISc Bangalore in June 2020. His research interests lie at the intersection of game theory and machine learning. In particular, he works in the fairness in online learning, strategic learning, information design, and fair division. We request the audience to keep your microphones on silent for the duration of the talk, except when asking questions. And for questions, please feel free to unmute yourself and ask directly or type them in the chat box and we will relay your questions. Over to you, Professor.
Thank you. Can you hear me, the audience here? Also, the audience online, I'm not sure, I can't see them. So they're, I can hear them. Can they hear me? That's okay. Okay, let's assume that. So, okay, so thank you and everyone for calling me. So today I'll speak briefly about learning in the presence of strategy. In particular, when self-interested agents either make decisions that are in their best interest, and these agents interact with some decision-making system. In particular, the systems we are going to consider here are machine learning systems. Okay, and that's why the title "Learning in the Presence of Strategy." Okay. All right. So here's a classical machine learning view. We have a data that's given to a machine learning system, and that system makes some decisions. Okay, whether it's classification, regression, whatever it is, supervised, unsupervised. The machine learning system, however, does not take into account that the decisions that these systems are making actually affect individuals, and these individuals could be strategic. In particular, consider an example of a bank who has to decide who gets a loan based on the features that they have, the individual's features. Another example is, I'm sorry for this thing here. Another example is deciding health risks, right? Providing health scores to individuals based on their data, previous medical history data, and so on. Okay, so how does agents behave strategically in a way that adversarially, possibly adversarially, affect the learning mechanisms? Here the applications are healthcare, banking, and then corporate hiring, and so on. Think of this. So we have a data. The data is used to train our model, right? This is a natural sequence of things. This model is deployed in let's say a bank or education system or wherever, and then these systems interact with agents. In banking, individuals apply for loan, and then there is a system that decides whether a person should get a loan or not. And that system, or whatever, consider a classification rule. That classification rule is trained over millions of past users' data. All right. So this is the view we are looking at. So here's what gaming happens. If the agents know these rules, if the agents know classification criteria, then agents might present their features in a way to get a favorable outcome. For example, if agents want to get a loan, then they can present their features in a way that they are more suitable for a loan under a given criteria, right? That need not, in particular, that does not improve their qualification per se. Okay, right. So here's another example. It's a credit scoring, banking credit scores, essentially a threshold-based classifier, health risks, and so on. Okay, so here's a classical a phenomenon called as Goodhart's law, which states that, let's look at the this rainbow colored plot here. This is the objective that we care about. This is basically students' performance in an institute, for example. Okay, and this is a proxy for that objective. Okay, a proxy is something that we can measure and optimize. Things like grade points, GPAs, and so on, things like that. Okay, so this is performance, and this is the GPA, or maybe this is some sort of health indicators. These are health indicators, and these are some sort of a hidden objective, right, related to health. This is objective we care about, and this is the proxy objective we know how to optimize. What happens is that when this proxy objective becomes a goal, then this proxy objective is not a good measure at all. So this is Goodhart's law. Goodhart's law suggests that when a measure becomes a target, or measure becomes a goal, it no longer stays a good measure of something, right? So people realize with time that they need to optimize over this criteria in order to maybe get loan or something else, in order to get favorable outcomes in general. And what happens is that this objective that we really care about, we do really worse with time. Okay, here's another very related effect. It's also called as Cobra effect. There's a story to it. In 18, I think, second half of 18th century, 19th century, British were moving from Bengal to New Delhi, and they had this trouble that the New Delhi, the cantonment there, area there was full of snakes, cobras in particular, and British were afraid of this foreign animal. So they came up with a scheme where an individual gets a certain fixed amount of money if they come up with a dead cobra. Okay, a bounty for dead cobras is the scheme. However, people started breeding cobras in their backyard. So this is how we look at gaming in particular, right? When agents are not, their incentives are not aligned with the objective, then they are going to take an action that maximizes their payoff, irrespective of what the system's payoff is. Okay, and this adversarially affects systems, or we will consider settings where it adversarially affects systems. Okay, it need not in general, but we'll consider the settings where it does. Okay, so here's a difference between a classical classification rule. We can consider, instead of classification, we can consider ranking or some other learning rules as well. But let's instantiate this learning thing with classification rules. Okay, so a classical classification rule versus strategic classification rule. The most important difference is that the data that a classifier is trained on is no longer the data, is no longer the same distribution from which your test data comes. Okay, the test data in particular, so consider for instance a loan data. The training data is coming from, let's say, distribution D train here, whereas test data is a result of two factors. One, the training data, the natural law that which generates the data. Also, the second factor is the strategic factor, where agents respond to the classifier, and this classifier induces some shift in the data. Okay. So distribution is not same. Training distribution and test distributions are not same. Okay. All right. So test data is obtained from a classifier F and the training data. Here's a game theory interpretation of the same. Think of two players, a system maybe we call it algorithm, or in classical literature it's also called a jury versus contestant. So a system and users. Okay, we'll consider only one user, but that could be multiple and so on. So they play a following game. System learns some classifier F from a training data D. System makes F public, and we will talk about this aspect a little more. For now, let's assume that the system makes F public, and a user, which is second player, observes F. This is a sequential game, one shot sequential game. User observes F and reports her feature to obtain desired outcome from F. In particular, a positive classification from F in a classification setting. Right? Okay. So the goal is for the system is to adjust to this distribution shift or the changes in the distribution as a result of strategic behavior by user. User essentially is simply playing a best response strategy. Okay, given F and given D, user simply misreports a feature that guarantees user a positive classification. Okay. However, if misreporting has no cost, then they can always have a best response that will guarantee them positive classification, right? So for example, in terms of in case of health score example, everybody will report highest highest health scores, okay, highest indicators for their health score. So we'll assume that it comes with at some cost, and then that becomes a non-trivial optimization problem. Okay, so users want favorable outcome. Users utility, to just to put it in numbers, is 1 if they are classified positively and 0 otherwise. Systems want to predict the true label accurately, and let us look at the user's best response to classifier F. So users see F, and X is the feature space. Users respond to F by misreporting X. So user's true feature, let's say user I's true feature is X, and user is anticipating to respond to F by X prime. Okay, so F is a classifier here. So if F of X prime is either +1 or -1, and C is some cost. So C represents cost to misrepresent X as X prime. Okay. So users solve this problem and come up with delta F of X. Right. So if this is, let's say this is +1, we'll make few assumptions. We'll also assume that cost is non-negative, misreporting is costly, and truthful report incurs 0 cost. Okay. So one of the best responses when for all those users that are classified positively is a truthful response. Right. So only those who are denied loans are incentivized to misreport. Those who according to F, those who get loan are not incentivized to misreport. Okay, cost or otherwise. However, agents who are denied loans are incentivized to misreport, but they cannot misreport arbitrarily. There is a cost associated with that, and they misreport only if it is if 1, they get a positive classification out of misreporting, and 2, that the cost is not too large. Okay, this is the simplest version of it. We can always add some constants here and okay. Yeah. they know f, they know all the parameters that define f. This is the assumption here. We'll go to that. Yeah. Of course, there are settings which consider. Okay, we'll consider them after 2 slides. We'll consider. We'll relax these assumptions in some time. The system's payoff is this, the accuracy. We'll consider error. Notice the difference between the the strategic classification rule versus a classical classification rule. The difference is here, right? F of delta f of x, which is agents are responding to f under this. All right. Throughout this talk, we'll consider a simpler class of cost functions. Notice that cost function is defines the cost of misreporting for the agents. So we'll focus only on separable class, which says that cost is non-negative. Of course, the second point here is that the cost does not depend on how you arrive at y from x. Okay. So there are two functions, the C1 and C2, and the cost depends on its value, C2's value at the misreporting point, and C1 at true value. Okay. It does not depend on how you arrive at y from x. It does not depend on that sequence. And this condition essentially guarantees that if we have guarantees that truthful reporting is a best response when you get positively classified. Okay, or it's zero cost. Truthful reporting has zero cost here. Okay, so let's consider one example. This is a simple example. C2 of y is equal to C2 of C1 of y, which is simply an identity function, and there is some alpha here. Okay, so that's and then plus represents that it's non-negative quantity. Okay, so let's look at this figure. So we have f here. F represents some classifier. The gray region here represents a positive class, and outside of this is negative class from f, negative decisions from f. Now let us look at x here. So let's say that x represents some user who is of course x is classified negatively in this. It does not get a loan. Now x lies on this boundary, which defines a boundary for which is defined by alpha, and there is some distance from this point, the tangent here, such that if x goes to y, x is indifferent between so it's x is exactly at the boundary, right? So any agent in between this in this annulus is incentivized to misreport. Okay, so any agent on the line xy will represent the features as y, misrepresented y. Okay, in fact, because our cost function is separable as this form, there is no cost of misreporting from this point to this point. Let us now consider x prime. X prime can always do this. X prime can always go from this point to the perpendicular point here, and then move along this line. Right? That movement is cost free because we have a cost function like this. Okay. All right. So as far as the agents are concerned, for the costs, f and f prime are equivalent. Okay, both these classifiers are equivalent as far as strategic classification is concerned under separable costs. Okay. Any questions here? Right. So clearly f prime, f prime will have more error. What we want to see is that given sufficient data, can we make f prime's error as close to 0 as possible, or is it we'll come to that in next slide. Okay, so here are few definitions. So in this example, we considered a simple version of the cost function. Okay, now let us go to a separable, more general separable cost function. So there are two cost functions. So two C1 and C2s. Let us define cost threshold classifier as a classifier which classifies if Ci of x is greater than or equal to some fixed number t, classifies this as +1 and otherwise it is -1. Rademacher complexity is the standard thing. I will not explain this. All right. So here's the algorithm for strategic classification for separable case, separable cost case, more generally. This algorithm is an extension of the figure that we have seen. What we need to do essentially is to consider an appropriate f prime which is equivalent to f, right? And then in the figure we have seen that since f prime is equivalent to f, all we need to do is look at the class of linear classifiers here, right? And then the problem is essentially to find an appropriate shift of that linear classifier. We also know that it has to be perpendicular to alpha, right? All we need to look at is the shift, and this is simply an extension of that. What shift we should use? We should use empirically the shift that gives empirically the largest highest performance empirically, okay, the largest accuracy in this case. So here's a empirical risk minimizer, okay, that minimizes an empirical risk given that we manage the shift, okay, we adjust for the strategic shift, all right, and then we use C1 and C2s appropriately. If C1 is equal to C2, which is identity, then everything goes exactly the same as we saw in the example. Okay, so here's an important result. So let R be the Rademacher complexity of a class concept class H. M is the number of samples used to construct F, right? And delta is the probability with which we need. Delta is, let's say, a number between 0 and 1, represents probability. So then with probability at least 1 minus delta, we get a accuracy of a classifier to be at least the accuracy of the optimal classifier under this class for any distribution and any separable cost function C minus epsilon, okay, and this holds for any epsilon. So for every epsilon there exists large enough M, that is the number of samples, such that you can reach the optimal as close as epsilon to optimal, okay. So that's the result. Okay, so as it was pointed out earlier, that agents may not have access to F, right? Agents do not know Banks' true classification criteria. However, agents may have access to decisions by F. Think of a social network where agents see their friends and friends decisions, loan decisions of their network, okay, on their network, right? So agents have access to the decisions by F, and there is one interesting example here. So Schufa is a German agency that provides risk scores, financial whatever we have, CIBIL scores and so on, right? So they provide these scores. Open Schufa here, it's a open source platform. What they did is they looked they looked at thousands of individuals who applied loans and the result they got from Shufa. Okay, so their goal is to sort of reverse engineer and reconstruct Shufa's classifier. All right. So what OpenShufa does is provide recommendation to people how to apply loans so that you stand better chance of getting them from Shufa. Okay, so this is an attempt to basically find out F as close as they can. All right. So a strategic error then is given by this formula. Right? So you have a true label and you have F hat, which is now is not equal to F, but F hat is some estimate of F. Right? And so basically, who is in the dark here? Which is strategic classification in the dark. On one hand, the bank or the system basically tries to keep F secret, in the sense that F is not known to the agents. However, agents, the information about F leaks via F hat. Right? Agents see the outcomes of the loan applications of their friends and so on. So agents basically respond to this F hat, which may not be a accurate description of F. Okay. So on one hand, systems might believe that a secret classifier is harder to game. Okay. Whereas on the other hand, system loses control in the sense that a secret classifier's response by the agents is also in the dark. Agent also cannot anticipate properly, or the system cannot anticipate properly the response to that F hat, which agents are constructing by themselves. Right. So if agents, if the system is transparent, if F hat is replaced by F, then system can adjust better, right, to the agent's responses. However, if not, then we have no idea why system is better off by keeping this decision secret or this classifier secret. Right. So by making F public, system can better anticipate the agent's responses, and on the other hand, by keeping F private, system is in the dark. So both the agents, well, the agents can't see system's classifier, agents are in the dark. System cannot anticipate properly the agent's behavior, system is also in the dark. So both of them are in the dark. Okay. All right. So here's a simple figure that represents what's happening here, right? So let's say that F is a system's classifier. System came up with F. Let's assume for simplicity that F is linear classifier, and this dotted line represents a cost boundary, which means that every agent in this annulus is incentivized to misreport to the classifier boundary. Okay. And F hat is, so F is a secret classifier now. F hat is the one that is constructed by some agent in the system, and this agent responds to, so let's say agents look at their friends' decisions and construct some F hat. F hat is close to F. However, F hat is, so agents respond to F hat and not F. Okay. So this region S is a region where F and F hat do not agree. Now let us look at what happens in a strategic case. The red dotted line here represents a cost annulus of F hat. Agents in this are going to game the system, are going to misrepresent their features. Now the region E, in particular E minus 1 1 here, are those set of those agents that that will let me see, that will be classified positively, okay, by f hat. So that side is f hat, and are classified positively by f, but they game the system, right, at a cost. Similarly, E1 minus 1 are also classified positively by f, but are not classified positively by f hat, even with gaming, okay. And H is a true classifier here, and these two regions where H interacts with these two, E1 minus 1 and E minus 1 1, these two regions are the ones that are interesting, okay. This we will call it as E minus. So when a probability mass on this is large enough, then we say that it is recommended for the system to make F public, okay. So when probability mass of on E, in particular E minus, is large enough, then we recommend the system to make E public, make its classifier public. Otherwise it is better to have classifier secret, okay. So that's okay. So we want to evaluate this. So this is simply the difference between the error of a secret classifier and a strategic error of a classifier that is public, okay, right. So characterization result here says that if we also write epsilon precisely, but I'll avoid that here. When we have that the probability mass on the set E is large enough, then price of opacity is strictly greater than 0, which means that then it is recommended for the system to make its classifier public, okay, make its classification rule public. All right. So let us look at this from with some experiments. So this is price of opacity. This is always, you can see that this is always non-negative. By the way, theoretically speaking, price of opacity could be negative as well. There is no condition that tells us why it has to be, but it has to be non-negative. However, if you increase m, so let us say that m is the number of samples used, number of IID samples used to construct f hat. Okay, so f hat is constructed as follows: we consider x coming from some distribution, and the labels are given by f. Right, these are the decisions made on these individuals. X represents individuals. F hat is just get IID m IID individuals and construct a ERM, SVM, or any empirical risk minimizer. That's how we get f hat. Okay. So now we use several classifiers. This heart is the one that we discussed earlier for separable cost functions. SVM is support vector machines. So when we see that the SVM classifier, a non-strategic version, gives the largest accuracy, the smallest error. Okay. However, if we use SVM with the this thing, the error shoots up. Okay, we use SVM with fully informed, the error shoots up. When agents become strategic, our classification rules that are not adjusting for this strategy will give you large error. That's everything is in between, right? The price of opacity is non-zero, which means that if you look at the Hart's classifier that adjusts for strategy, for certain class of cost functions, and you will look at SVM in the dark, I'm sorry, if you look at Hart's fully informed classifier, which is this, which represents that agents are adjusting to this uh, using F, full knowledge of F. Right. So, in the dark versus fully informed, the difference is price of opacity. This difference goes down, I mean, almost linearly as m increases. So, for m maybe 10 to the power 4 or so, there is no difference between making f public versus making f keeping it secret. It's almost always a common knowledge. However, it is important to see that when agents do not have sufficient information about a classifier that is employed by a system, it is not good in general to make this classifier secret. Okay. You should always keep it transparent so that you are here and not here. Okay. Yeah. So let us look at another sort of version or another variation of this setting. We assume that agents manipulate the system. However, the agents labels, true labels, are not changing, right? They are either qualified or not. The way, even if they are manipulating their features, they don't really manipulate their labels, true labels. I mean, these don't change as a result of even costly manipulation in their features. Okay. But however, think of a system where you have uh, um, costly manipulations that may result in changes in the true labels. For example, students taking additional courses, right, in order to improve their GPAs and so on, or maybe tuitions and things like this, that may have certain effect on though debatable, on their true labels. Okay. So let us add. Let's try to remove this assumption. In this, the distribution changes. Sorry for the typo here. To d theta, right? So when we are using a rule theta, the distribution d changes to d theta, and this d includes x, y, both both features as well as the true labels. Okay, so this represents performative risk, which is simply I'm using loss functions here. Uh, Earlier it was just 0 1 loss, and here's an iterative version of the same problem. Okay, think of this happening over multiple rounds. At each time t, you have some parameter theta t that describes your model, and you look at samples from a distribution generated as a response to theta t model, and some loss for this under this, and you calculate the next iterate to be the minimum loss thing, right? This is the empirical risk minimizer that we are talking about. All right. So what we do is we look at performatively stable rule f. Okay. So thetas are the parameters of this rule. So that is performatively stable because it is the best response to the distribution induced by itself. Okay. So it is a equilibria in some sense. Okay. All right. So I'm again going to go a little faster here. And a result here is that if you consider L to be smooth enough, in the sense that it is strongly convex and it satisfies some smoothness properties, and D is sufficiently Lipschitz, that is Lipschitz with respect to thetas. If you don't make parameter values, if you don't change parameter values too largely, the distributions induced by these parameters are not wildly changing. Okay. So under this, the repeated risk minimization rule, which is given by this, converges to a performatively stable at linear rate. Okay, so we can achieve this, we can achieve performative stability by repeatedly doing this, okay, at a linear, so we can go as close to performatively stable. However, our goal is to find the optimal one in this sense, okay. And again, under strong convexity and Lipschitzness, Lipschitz condition, we can say that the stable points are close enough to the performative optimal points, right. So in the previous slide, so these stable points, when loss function is smooth enough, it is strongly convex and so on, and this distribution maps are Lipschitz, then we can say that performative risk and performatively stable rules are also uh, the minimizers of this performative risk to a certain additive flexibility, right. Okay. Okay, so let me summarize this. There are several other settings here, but first thing is that, first takeaway is that traditional machine learning models may perform very badly in a strategic setting. Okay. The other extreme, which we didn't discuss, is to overfit to strategic nature, right. So maybe we are anticipating strategy from everyone, which is not true. Then we tend to overfit to this, right. That again may result in errors that we don't anticipate really. We have also seen that the strategic classifiers are learnable. So at least under some conditions and on cost functions and so on. And then there are many questions here. First question is, we have assumed that the agents are homogeneous. Everyone responds exactly the same in an exactly same manner to a given classifier. If they know the classifier, their response are predictable in some sense, which is not true in general. There are several reasons. We didn't discuss social burden. A social burden, to be a little more specific, is an additional cost a positively labeled individual has to pay to get positively classified. That's a social burden, which means that the classifier F induces an additional burden on the qualified individuals. Okay. So to see this little, so I can continue. So imagine that just a single dimension. It's one feature. Individuals are, so this is a positive class, this is negative class. True labels, everyone which has positive thing are have true labels positive, and everyone below 0 is negative, right. This is simplest example. A classifier that's optimal classifier is just to put have boundary here, right. However, this is not strategic optimal. Strategic optimal is somewhere here, right. So that everyone in this boundary will misrepresent themselves, and all these points on this line will be here. So as far as the classifier is concerned, classifier sees these points and not these, so this is hidden from the classifier. Okay. So this, the cost incurred by the points in this region or individuals falling in this region, in order to get a positive classification, they have to work extra, they have to pay this cost, right. That's a social burden, and we didn't discuss social burden in today's topic, but this is relevant. Yeah, yes, yeah. No, the costs limit that. So cost has to be between 0 and 1, right? So agents, for example, these agents are also classified negatively, but these agents don't misreport because it's too costly for them. So if you make this boundary here, then again there will be an annulus of individuals that will misreport. But then that's not an optimal, because then there is, yeah, additional point. Okay. Yes. Yes. Mhm. Yes, yes. So there are, that's true. When we have a one-shot game, the overfitting is a problem, which may not be as big a problem when we consider multiple interactions between system and agent. Uh, However, I'm not sure. Uh, I mean, we need to quantify this. Uh, how much of an effect like initial biases have? Like initial. So, for example, initial assumptions will have some effect in the long term. We're not sure about that. Right. So, however, in the first game that we saw, Stackelberg game, where there is an individual, there is a system and there are agents. The agents respond to system's classifier. The system may end up overfitting to the strategic nature of agents. Yeah, but again, in multiple interactions, it might yeah, smoothen out. Okay, so social burden, information disparity. Are individuals with larger information about others better placed in the system, right? So are they, is information the key to get positively classified? How does it affect others in general, right? Herd behavior. So this in particular is relevant when we are considering the data coming online, right? So think of systems such as recommendation systems, where individuals see past data on purchase decisions by others, and this may lead to selecting suboptimal choices following the decisions made by others, even though these agents made strategic decisions, rational decisions. Okay, it may happen that all the future agents' rational decisions turned out to be an suboptimal decision. Okay, that's herd behavior, following what the early few agents did. Um, that that's also an interesting question. Beyond classification, there are tips such as online learning, clustering, ranking, recommendation systems, and so on. We looked at systems where we looked at settings where uh, agents manipulate, and system where in a way we are taking system side. Right? So we're trying to find out a classifier or a learning rule that is robust to agents manipulation. However, the other version of the problem also exists, where the system sort of provides or generates rule that make decision makers, that are users, to make favorable decisions. Okay. So, for instance, in persuasion or something called as information design, the system wants to make the users take a favorable action, maybe purchase decision or voting decision or I don't know, whatever, and can provision information to the users to do so. Okay. So there is an instead of there is a information disparity between the two. The system has more information about some ground truth. Okay, maybe knows the ground truth, and then the users, the decision makers, do not know this ground truth. However, they have some prior about this ground truth, and the system releases some signals to the users, and system can design these signals in a way that the rational user, which takes the decision based on the posterior, makes favorable decisions, favorable to the system. So the system might also be strategic in their in its behavior and manipulate users. Furthermore, strategic representation setting is the one where system tries to kind of compress the data and show the representative data of a large pool of data sets to the users, and system can be strategic about this. Okay. So now we are taking user side and say that when the system, which has large pool of data and is selectively assorting the data to show as a user what is the best learning strategy. So it is again learning in the presence of strategy, but here the strategic component is the user, is the system, not the user. Okay, so that's I think that's it. Thank you. I'll take any questions. Maybe someone online.
Let's all thank the speaker. Thanks a lot, sir, for an informative talk. Any more questions?
Yeah, yeah, sure. Uh-huh. Okay, I think the main difference is the distribution. It's not the noise that we're modeling, right? So it's not any sort of distortions or any. We know these f's exactly. We know these distributions exactly. Let's say we assume that, right? Even though this problem persists, the strategy problem, even if f or the distributions are known exactly, completely, they're still there. It's not that we're adding noise with a certain structure. Okay. Yeah, so that's one. The second point is that here more often we do equilibrium analysis, which sort of is missing from that. I'm not sure much about that literature, but here we are more interested in the accuracies in the equilibrium. So, for example, if we look at performative prediction setting, we are interested in a performatively stable equilibrium. So that's the point which is of interest to us, and we'll look at we'll evaluate classifiers that are performatively stable, which I'm not sure whether distribution
Another
robust
one thing
learning
is that you have shown one simulation plot.
Yeah.
So regarding that, where you are finding f hat,
Yes.
how like I have some doubt on how are you finding this
Yes.
f hat, because initially we have this setting where you have an f, you have a d train, and you have a d test, which are different
Yes.
from each other.
Yes.
And now when you're using to find f hat, which
Yeah.
data are you using to get the features from
Right.
your f,
So-
so that you find f hat?
So I get this from data set D.
Yes.
Okay. So let's call
Agree.
it train, where anyway is not changing.
Yeah.
However, yi's are not these.
So
This is my data set.
but it will
compute
be
f
the
hat.
same data set, or it will be different?
No, it is different. It's different. These are just m IID samples from this.
So to find a f hat, you are taking
I'm
independent
taking
samples
the
from d train
decisions by
itself.
f as labels. I'm taking decisions by f as labels. No, so I know this data. I know this data. This f of xi's are going to be either 1 or negative 1. So think of it really as a social network, right? So I look at my friends and friends and look at their features, and they applied for loans, let's assume, and whether they got loan or no. That represents this.
But in that setting,
Yes.
it would be like you're trying to find f hat
Yeah.
from your features x, which are like from a different distribution, like d test.
Oh, so this is essentially we are just separating these two. Okay, so we're just considering d train and d test on feature space, not a joint space. Maybe that's giving different. Yeah, no.
because inherently I was thinking
So you can
that
think of this is trained on like just on feature space. Okay. So the goal ultimately is to basically estimate this.
because the idea that I was, if you are using the same data set d train
Mhm.
to find f hat,
Yeah.
you will be pretty closely approximating f. But whereas if you are using some different, you are using features x from coming from a different distribution,
No, so
then
these
you will
are
be learning.
these are again coming from the
They're from same distribution.
yes,
Then it will be
yes,
like
yes.
so that's the main
Just
doubt
that the
I had.
label is different. They are
Yeah,
labeled
label
as
will be different, but
yeah.
data will be the same.
Data will
So
be the
then
same. Yes.
yeah. And another one small question is
Again,
that
non-strategic.
yeah.
Yeah,
So
not
now
delta x size.
rather than anticipating your if your f is assuming that your f is public and you are anticipating what the agents might do
Yes.
to get a
Maybe I
better
don't
outcome.
need this, right? Okay.
To get a better outcome, and then you are changing what's you are strategically positioning your f such that those who are not eligible, they'll become not eligible. So like in that simple example, then is there a way to incentivize the truthful bidding or truthful features rather than choosing, because like for example consider victory auction, there you are actually, it's in your in the agent's interest to truthfully bid. So can we do this kind of problem in that variant?
Thanks a lot once again, sir. So we have arranged refreshments at Coffee Hut. Please feel free to continue your conversations while having tea. Thank you all and have a great evening.